joining us. While we wait for the live stream to start, I'll just remind you that we have a code of conduct at our events. So if anything is going on that makes you uncomfortable in the chat or anything else, feel free to reach out to us. You can either email Leah or you can message one of us on Zoom, and we'll make sure to respond to you. So Leah, please let me know once the live stream starts.
We're live.
Awesome. Okay. Good evening, everyone. Thanks for joining us wherever you are, on Zoom, on YouTube. It's great to have you here, and welcome to our October public lecture. This month's speaker is Dr. Emily Petroff. So just to give a brief introduction, Emily finished her PhD at the University of Swinburne, Swinburne University of Technology in Melbourne, Australia. Then she moved to the Netherlands, where she did 2 postdocs, one of them at the Netherlands Institute for Radio Astronomy, and the other at the University of Amsterdam. And since 2020, just last year, she's been with us here at McGill University and the McGill Space Institute, where she works with the CHIME collaboration. So Emily will talk to us about fast radio bursts. I'm very excited to learn about them, what they are, where they come from. If you have any questions at any point, you can either write them into the chat. If you're on Zoom, you can also ask to unmute, and you can unmute and ask your question to Emily live. If you're on YouTube, just write your question in the chat and we'll make sure to pass it on to Emily. So with that said, Emily, please go ahead.
Great, thank you. All right, so I hope you all can hear me, and thank you so much for joining us today. This is very exciting for me to be able to give a public talk. Normally I would be live and we'd be in the same room. Hopefully I would be able to get you excited about what I'm talking about, but hopefully I can recreate the magic over Zoom and maybe even reach a few extra people who maybe wouldn't have been able to make it otherwise. So thank you for joining us, and thank you, Simone, for that great introduction. So yes, my name is Emily Petroff. I am currently working jointly at McGill and at the University of Amsterdam, and tonight, I'm going to be talking to you about something very near and dear to my heart, which is fast radio bursts. So I'm going to be talking to you about this very interesting, kind of mysterious phenomenon that even us astronomers, we still don't really know exactly what they are, where they come from. I probably will leave you with more questions than answers, but I think that's the way any good science should be. So we can just get started. All right, so tonight, I'm going to be talking about these things called transients. So in, just normal English language, transient is something that lasts for only a short time or is impermanent. But in the context of astronomy, an astronomical transient typically is something very short and energetic. So, it's not necessarily something like a galaxy that lives for billions and billions of years, changes very slowly. We're talking about some of the shortest, most extreme events in the universe. So we as a human race have been looking for transients since basically forever. The very first transients we ever spotted were these things that we called wandering stars. So if you look up at the night sky and you look that there are some particularly bright stars that seem to change with respect to the background stars. They don't always stay in the same place. And I'm sure you can guess what these are. These are the planets of our solar system. They're not fixed in the same way that the stars are. And also, transients have played a big part in our own history. So for example, this is the Bayeux tapestry from commemorating the Battle of Hastings in 1066, and actually woven into this tapestry is this very interesting feature here. It's something everyone's pointing at, and the text actually says, "These men wonder at the star." And this was, in reality, was a comet. And that comet, they thought that this had some sort of was telling some story about what was going to happen in the battle or something like that. But this transient phenomenon in the sky was very important in the context of this particular point in history. And also maybe getting into more specific types of transients that I'm interested in. This is a very interesting text from an old Chinese history text from the year 1054. And the highlighted passages, I'm not fluent in Chinese, so I can't actually translate for you, but these highlighted passages specifically deal with something that they called a guest star, a star that appeared in the night sky and in the daytime sky very brightly, and then over the course of several days diminished in brightness till it was gone. And they did such a good job recording this that actually years later we could, centuries later, millennia later, we could go back and look at the rough position on the sky that they described. And in fact, there we find the Crab Nebula. So this is maybe an image you've seen before, but this is a very young supernova remnant. So in the year 1054, the star that lived at the center of this location went supernova and exploded. And all of the material from that star started propagating outward, and you see this beautiful nebula that's left over. But what's particularly interesting about this, and that plays into the story that I'm going to tell you about tonight, is that at the center of this nebula there's still a star. There's something left over from that explosion. This very bright, this is taken in radio imaging, this very, very compact and very extreme type of star called a neutron star. So when that star exploded, some of the remnants actually collapsed to form something very dense. And it lives in this extreme environment where, it's got a lot of material swirling around it. And this is, we'll get back to neutron stars and to pulsars specifically very soon. But I think this is a really interesting example of our historical fascination with the things that change in our night sky. And that's something that still really rings true for me today. And as our telescopes have gotten better, so previously these transients that I've talked about were all what we call naked eye transients, things that you could see in the sky without a telescope. And now we're starting to probe further and further into the universe using much more sensitive instruments. We don't just use our eyes anymore. We also use instruments like, for example, these are the 10-meter Keck telescopes in Hawaii. And the more powerful the telescope you get, the more sensitive it is, the further back you can look into the universe, essentially. So we live, hopefully you're familiar with this, but we live in this universe that is not only expanding, but accelerating in its expansion. And as you look at objects that are further and further away from you, you also are looking at things that are further back in time, further back in the universe. The light you're receiving is coming from things that are that happened, billions of years ago. And so as we start to look in a much more sensitive way, we look at galaxies, we take pictures, we take images, but we also look for transients. And we are starting to explore this sort of space of astronomical transients as we look further and further back in the universe. And we can do this in a lot of different ways. So there are many different types of light. There's the visible light that we see with our own eyes. There's a more energetic light like ultraviolet, and then X-rays and gamma rays, which don't penetrate our atmosphere. There's infrared light, microwave light, and then the sort of lowest energy is radio. And we look for transients in all of these places. So I've highlighted a few here. We see in the visible spectrum, we see supernovae like were described in the historical texts. In the X-rays and gamma rays, we see very bright short transients called gamma ray bursts. And in the radio, we also see transients. And these are the kinds of things that I want to talk about today. We're starting to also, I will just briefly mention, we're also starting to explore an entirely different kind of spectrum. We have the spectrum of light, but then we are also starting to talk about and starting to look at the gravitational wave spectrum. So maybe you've heard of the gravitational wave detectors that we have spread across the Earth that are now detecting gravitational radiation, which happens when two compact, very dense objects start to orbit each other. And this is also a very interesting type of talk. I won't get into gravitational waves in this talk, but I do want to highlight it because now we're looking for transients not just across the spectrum of light, we're also looking for transients across the spectrum of gravitational waves. So astronomers are getting much more creative in where we look for transients. But the ones I want to talk about today specifically are focused in this radio wavelength. And these are these things called fast radio bursts, or FRBs. So I'll probably use these two things interchangeably throughout the talk. Most of us in the community that works on this, we just call them FRBs. But every time I'm talking about these things called fast radio bursts, and I'm going to explain sort of how we learned about them, what we know about them so far, what we don't know about them so far, and where we're trying to go. So fast radio bursts have a very interesting story, in my opinion, and it's one that's really I enjoy telling it. So I'm looking forward to kind of giving you this story. So the story of FRBs starts in 2001 with the Parkes Radio Telescope in Australia, where I did my PhD. And when I say the story starts in 2001, it actually kind of starts in 2007 because we'll get back to it in a second. The actual first fast radio burst was in data that was taken with Parkes in 2001, but that data wasn't searched in a way that you could see fast radio bursts until 2007. And in that data, we were actually looking for something totally different. We were looking for these things called pulsars. So if you're not familiar with a pulsar, I mentioned it before, that thing in the middle of the Crab Nebula. A pulsar is what's left over when a big star explodes and goes supernova, and there's this very dense core that remains. Not dense enough to form a black hole, but dense enough to be this very compact object. What's interesting about pulsars is that for reasons that we don't really know, we still, after 50 years of studying them, we don't know, they emit these very strong radio beams out of each of their magnetic poles. So you can see the magnetic field here, and then this is this radio beam that comes out of the pole. And as the star spins around, you see it essentially like a lighthouse in the sky. So if you're looking at the pulsar in such a direction as you see the beam as it goes across, every time the star rotates, you see a pulse. And in practice, this looks something like this. So this is I'm about to play a movie of a pulsar that we observe quite regularly with the Parkes telescope. And here you see that there's individual pulses from this pulsar that we observe. And this pulsar, so these are very extreme objects. This particular pulsar is spinning 11 times a second. This thing is about 1.5 kilometers in diameter, and is spinning, 11 times a second. I don't think even I couldn't do that. And we actually have pulsars that spin thousands of times a second, which is actually faster than most kitchen blenders. So we have these very energetic, massive, compact stars that are rotating extremely quickly. And every time the beam crosses our line of sight, we see one of these pulses. And we've been studying pulsars now for about 50 years. And oftentimes when we study them, because they're so regular and periodic, we often just study them as we just fold all the pulses together and study them since we know the period. But there are some pulsars that aren't quite as regular. So this is an example of one that gives off these things called giant pulses. So the actual normal emission of the pulsar is kind of buried here in the noise, but every once in a while, it gives off an extremely bright pulse. And here you see a perfect example. And these pulsars are actually best studied if you search and look for their single pulses rather than summing all of the pulses together. So we search for these and we look at the data in a slightly different way. And in doing that, we were trying to find more pulsars that give off this kind of emission. We were trying to look for ones that look like this, since this is a fairly understudied phenomenon. We still don't quite know what produces these giant pulses. And in doing so, astronomers who are using the Parkes telescope were searching for new pulsars in the Large Magellanic Cloud. So this is one of the satellite galaxies of the Milky Way. And there are several known pulsars in the Large Magellanic Cloud, but they were looking for new ones. And they were specifically looking for new ones in terms of the single pulses that they gave off. Did any of them give off bright one-off single pulses? And so the way that they were looking, they were using this camera on the Parkes telescope that had, in the radio, it's not as nice as a megapixel camera. We had 13 pixels, each of these circles. And you can just basically tile around the entire Magellanic Cloud by placing these pixels in various places. And so they had these pixels here. And so not quite on the Magellanic Cloud itself. And in doing that, they actually detected something in some of these pixels. So very far away from the actual place where the pulsars live. And it was in these particular pixels that they saw a signal that looks like this. And this was very alarming to them, and I'll get into why. But it was then called the Lorimer burst. So it was a very bright single pulse, very similar looking to pulsar pulses. It lasted about 5 milliseconds, very quick. And it was so bright that it saturated the pixels. So we don't actually know exactly how bright it was, because it was so bright that it just saturated our detector. And there was only one pulse, and that's important. You know, we've looked and looked for more pulses from this, and we have not seen them. And what's really striking about this to a pulsar astronomer is this signal here. So we actually observe this sort of sort of trend in the signal for most pulsars. And what we're seeing here is a phenomenon called dispersion. So it's a little technical, but just to walk you through it, what happens with dispersion is that all of the radio lights, so you see all the different wavelengths here, I'll pause it, you see all the different wavelengths. These are some shorter wavelengths and some longer wavelengths. The idea being that they're all emitted at the same time from the source. But then they encounter some material in the Milky Way or in the interstellar medium, and that material acts kind of like a prism. So in a prism, you see the colors of light separated out because the different light takes longer to go through the prism, and the light gets separated by its color. So here you see that this light, the longer wavelengths kind of take longer to go through the material. And then in the end, what you get is a signal that looks like this, where the higher frequencies or shorter wavelengths arrive earlier, and the longer wavelengths or lower frequencies arrive later. And this is a known phenomenon that we see for pulsars all the time. But the thing about this particular one is that from that dispersion phenomenon, you can actually say how many electrons the pulse traveled through. The amount of the delay that you see is directly correlated, directly linked to exactly how many electrons were in the interstellar medium that it traveled through. So you can say, okay, we know exactly how much stuff it traveled through. And the problem with the Lorimer burst is that based on its location and how big this delay is, it traveled through something like 10 times too many electrons to be coming from the Milky Way or be coming from our galaxy and its satellites. We have a rough idea of how much dispersion to expect because we have lots of pulsars. We make a map of all of our pulsars, and we can actually see features in our spiral arms of our galaxy and things like that. But based on this pulse, the amount of electrons that it had to go through had to be much, much larger than anything we could explain with the Milky Way or the Magellanic Cloud or the space between them. It really had to be coming from somewhere outside of our galaxy. So this would be the first very bright radio pulse from outside of the Milky Way. My colleague, this is Dunk Lorimer of the Lorimer burst fame, said that it was unlike anything we'd ever seen before. So it's very exciting. They published the paper. Everyone was just very kind of scratching their heads, but very excited because, when you see something you've never seen before, all you want to do is find more things that look just like it. You really want to know more about this phenomenon, especially since there was just the one pulse. So there's not a lot to go on there. You want to find more examples. So when you want to find more, that involves doing lots of data analysis. And that's, for a grad student, when I was a grad student when all this was happening, that means looking through lots of plots. And a very, very clever grad student in the sort of cohort before me, Sarah Burks-Galore, did exactly this with lots of data from the Parkes telescope, looking for more of these Lorimer bursts. And in doing that, she saw something that looked like this. So people got really excited. They said, "Ooh, this looks kind of like the Lorimer burst." But the problem was, I mentioned that we look at the sky with several pixels. And when you expect to see something that's located, pinpointed on the sky, it should appear in one pixel. If it's very bright, maybe a few. But these things appeared in all the pixels of our telescope receiver. So that is not exactly what we would expect from an astrophysical phenomenon. If it's on the sky, it should only be in maybe one, maybe a few, but that was basically equally bright in all of them. And so Sarah called these the peritons, and these were named after a sort of a mythical creature. It's a winged stag that has the shadow of a human. So it's kind of a red herring. but called a periton. But the problem here was that it looked very similar in a few ways to the Lorimer burst. I had the same sort of, downward structure, but while the Lorimer burst was just seen in 3 pixels, this was in all of them. So, people they saw this result, and this was, we'd still just had the Lorimer burst. People saw this result and they started to get kind of disappointed. They thought, well, okay, maybe the Lorimer burst isn't real. Maybe it was just it was interference from near the telescope. We were wrong to think that this was something exciting and maybe extragalactic. And so we were in kind of a doubt phase for a couple of years after the periton results came out. But the nice thing about with science is that we get new data, and with new data, you can always, look again. So we got a lot of new data. And what this looked like was a brand new survey that happened on the Parkes telescope, where if you're looking at sort of the Milky Way here, we constructed a survey to basically look at the entire southern hemisphere sky in a way that we would be sensitive to Lorimer bursts. And we processed all of this data, and in just maybe a quarter of this survey of the whole sky, we actually had a very exciting breakthrough, which is that there was this paper in 2013 led by PhD student Dan Thornton, and they published 4 new Lorimer bursts, and they called them fast radio bursts, or FRBs. So this was the first use in the literature of the term FRB. And this is exciting, but what's more exciting is the word population. So it wasn't just the Lorimer burst, it was many, many different bursts. So they were saying that there's a population of these fast radio bursts spread all across the sky. And just from looking at these 5 events, the Lorimer burst and then these 5 Thornton bursts, they estimated that there were thousands of FRBs happening over the sky every day. Thousands. So they estimated a rate of something like 1 FRB happening somewhere in the sky, 1 FRB happening somewhere in the sky every 30 seconds, every minute, based on the fact that you might say, well, from 5, that seems a bit extreme. But at any given time, the telescope is looking at such a small patch of sky that given how small its field of view is, to see 5 means they have to be very common. And in fact, that's the case. We now know that fast radio bursts, their all sky rate is thousands per day. They are an abundantly common phenomenon. But at the time, we were getting quite nervous because this was, that was 2013. We started finding a few more fast radio bursts, but all of them had been found at the Parkes telescope. And that was very awkward because if they're real astrophysical phenomenon, they should be found at all telescopes. Every radio telescope looking for them should see them. So we were in a bit of a pinch. But fortunately, in 2014, the Arecibo telescope in Puerto Rico found its first fast radio burst. So we were very relieved. And that sort of tipped the scales, right? So we have 2 telescopes that have now seen fast radio bursts, and it was just Parkes that was seeing these peritons. So we started thinking, okay, well, the fast radio bursts are real astrophysical phenomena, and the peritons are just kind of a curiosity, kind of an anomaly. Let's move on with FRBs and keep finding them, keep looking for them, use more telescopes. And in fact, that's what we've managed to do. And now we are doing spectacularly. So, starting in 2007, our very first fast radio burst, and then 2013, we started to pick up the pace with the Thornton discovery. And now we're actually approaching something close to exponential growth in how quickly we find new fast radio bursts. And we've seen several exciting results in the past many years. Particularly, I would say in 2016, one of our most exciting things that's happened, we saw our first fast radio burst that repeats. And this was wonderful work done by Laura Spittler using the Arecibo telescope. This was our first repeating fast radio burst source. So far, we had been looking for them. We'd seen them just once. And despite lots of follow-up, I spent countless hours using the Parkes telescope to see if other fast radio bursts would repeat, but they did not. So they used Arecibo, and in doing that, they saw several new pulses from this one source, from the same position on the sky with the same dispersion qualities and all that. And that was critically important So not only are these things sort of mysterious one-offs, but if you have something that repeats, well, it can't necessarily be something that explodes. It can't be potentially can't be cataclysmic. So this actually gave us some just a wellspring of theories about what FRBs are, and we'll get to those in a minute. But now we call that source R1 because since 2018, we've now seen more repeating fast radio bursts. So in 2018, the CHIME collaboration published this one that we have since called R2. In 2019, there was a whole new array of repeaters. So we are starting to build up a population, not just of fast radio bursts, but of repeating fast radio bursts. It's worth mentioning, though, that not all of them repeat. We have spent basically the same amount of time on these sources that have repeated as other ones that have not. And some appear to repeat, some have tendencies to repeat, and some we have truly only seen the one pulse, and despite the follow-up, never seen another one again. So we're in an interesting discovery space. But it's truly an era of discovery, I will say. So, since from 2013 to 2019, we had lots of new telescopes on the scene to start looking for FRBs. And then from 2019 onward, we added some other exciting telescopes like Meerkat and Aperitif, but we have, these don't maybe look like traditional optical telescopes, but these are all radio telescopes searching for FRBs. And in doing this, we've gone from a population of 5 from the Lorimer burst and the Thornton bursts to 100, more than 100. And this is where we were at in sort of, the last couple of years. It was getting really exciting. And it's very clear that these are a real astrophysical population. They're coming from all over the sky. More radio telescopes are seeing them. That's a big relief. But for a long time in our community, there was still this sort of nagging doubt. And, people saying, well, what about the peritons? So this is my PhD supervisor, Matthew, and he would ask me this all the time. Anytime I came to him with a new FRB result, a new discovery, a new, a new analysis, he'd say, yeah, but what about the peritons? And this was really nagging at us because what if some of these fast radio bursts are actually just interference, or maybe there's something more complicated going on. So, we were really motivated to try to figure out this periton thing. And we got lucky in a few ways. And the reason that I say we got lucky is because we started looking in our data for the peritons specifically. We actually, as part of my PhD, I went through just so many plots of data specifically looking for peritons, even though we knew they were interference. So it was going dumpster diving, basically. But we were starting to build up a population of the peritons. I thought maybe if we had a population of them, we could kind of see, are they distributed in a certain way? Could we figure out where they're coming from? And we started actually finding the peritons in our data as it was being taken. And one day we saw a bright periton. And so we called up the site staff at Parks and said, okay, what was happening today? What was anybody working on, construction, or was there new equipment being tested or something like that? And they said, oh, no, nothing out of the usual, but you could always check the interference monitor. I said, okay, what interference monitor? It turns out that at the Park site, they had newly installed a sort of very low sensitivity, but large, sensor to detect interference on the site. And so this was important for a very specific reason, which is, if you look at the radio spectrum, we look over a range of radio frequencies. The actual Parkes telescope only observes in this shaded band here, sort of 1.1 to 1.5 gigahertz. But this interference monitor looks over a whole bigger range of frequencies. And so they told us, well, look at the monitor, and it's kind of coarse grained, but see if there's anything that happened at that time. And so at the exact time of our periton, there was this very, very bright notch of emission at 2.5 gigahertz. So we never would have seen it in our data. We never would have known that this existed. But because we had this interference monitor, we were able to, have a look and say, oh, okay, at 2.5 gigahertz. This was immediately suspicious because 2.5 gigahertz is actually the frequency where a lot of electronic equipment operates. Wi-Fi, cell phones, routers, things like that. I mean, none of those are allowed on the park site. It's a radio quiet site, but that immediately tells you, okay, it's probably something electronic on site, maybe like a poorly shielded wire or something like that. But as I said, we were also building up this population of peritons. We were starting to just look at a bigger swath, like bigger aggregate data. And so we could do things like what I did as part of my PhD, which is to say, okay, let's look at how they're distributed in local time. These are the FRBs for context. So FRBs should not care what time of day it is. They are in the sky. They do not care. And in fact, you see that they're, for the sample that we had, very evenly distributed across the entire sky, which is great. That's exactly what you expect from an astrophysical population. But if you look at the peritons, you see something that immediately stood out to me, which is that they are very highly peaked during business hours. And so this was actually time of day in Australian Eastern Standard Time. But if you correct for daylight savings, the peak actually gets stronger and gets more centered at a very familiar time, which is lunchtime. So I think you could probably figure out where I'm going with this. Maybe you know the story already. They came from microwave ovens. So it turns out you too can produce a periton at home if instead of waiting for your microwave to finish, when it's like 5 seconds away from dinging, you just open the door and you let out a little tiny burst of radio emission. And it's not harmful to humans. It's not enough to hurt you, but it's enough to make a very sensitive telescope think that it detected a pulse. So it turns out that you can make a periton in a microwave oven by opening the door when it's, before it's finished its cycle. So this is great. We solved it, so I could come back to my PhD supervisor saying, okay, what about the peritons? And I could say, no worries, they're only microwaves, and we can get back to FRBs. So the important thing here is, the big question that we had is, where are FRBs coming from? Hopefully you have that question too. I haven't really answered it, and I don't think I will fully answer it, but I will say that we have lots and lots of theories for where FRBs come from. There's actually even a catalog of all of the theories for FRBs at frbtheorycat.org. But just kind of looking at this list, this is a non-exhaustive list from a colleague of mine. You can see a lot of things come down to neutron stars. Pulsars, neutron stars, magnetars. There's some more like, esoteric things, sparks from cosmic strings, white holes, those kinds of things. But a lot of it comes down to neutron stars. And there's a reason why we kind of think this, which is, they check a lot of boxes for us. Pulsars mostly emit in radio wavelengths. They give off millisecond radio pulses. By nature, they're very extreme objects. The only kicker is that they're definitely not strong enough to be seen from other galaxies, at least the garden variety radio pulsars that we observe as part of galactic pulsar astronomy. We have 2,000 plus pulsars that we've seen in our Milky Way, and we've cataloged a lot of behavior from all of them. And the sort of garden variety pulsar is definitely not strong enough to produce an FRB from, millions to billions of light years away in another galaxy. So we have some questions. Maybe are FRBs cataclysmic? Are some of them cataclysmic? Is it something where there's an explosion and you just see one bright radio pulse? Are they repeating? In which case, there's theories that have been proposed where you have, a flare on something like a magnetar, or you have just a very extreme pulsar that lives in an extreme environment. Something like a very young pulsar, like the crab pulsar, maybe like 2 years after it was born or something like that. It's still one of our most extreme neutron stars that we know of, and it's 1,000 years old, which is young. But maybe when it was much younger, it had some much more extreme behavior. Or if you put a pulsar in an even more extreme environment, like orbiting around a black hole. So these are just a few of the theories that have been proposed for FRBs so far. But, we have evidence for both. We have this large population of FRBs that, we've seen once and never again. And then we also have the repeaters, which, they seem to indicate that they cannot be from a cataclysmic event. So, the situation, the data says we need more data, as is always the case, it feels like. So we still need more FRBs. So I mentioned that started from 2019 onward, we had this big army of telescopes that were looking for FRBs, trying to solve this puzzle, trying to get more data. And for the rest of the talk, I'm going to focus on this exciting particular telescope called CHIME, which hopefully you've heard of, but if you have not, I will tell you about it. So the reason why I think CHIME is so exciting is because, so I said we were kind of approaching exponential growth. And this was starting in 2016, 2017. And right around here, 2016, 2017, and into 2018 is where the CHIME telescope turned on and started looking for fast radio bursts. So what is CHIME? Well, it might not look like any telescope that you've ever seen. It is these 4 sort of snowboard half pipes. And CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. And it is located in Penticton, British Columbia. So it's a Canadian telescope, as you could probably guess from the name. And it was originally built to do cosmology, to do this experiment called hydrogen intensity mapping, which is using an all-sky map to search for remnants of cosmological signatures. But because it's a telescope that stares at the sky all day, every day, and has a really big field of view, it's actually perfect for finding fast radio bursts. So the way that CHIME works is it does not move. It has no moving parts, and it just stares up at the sky. And from all of these, along all of these lines here, we have lots of antennas. And those antennas produce lots of beams on the sky, lots of pixels. And the way that it works is that because it's just, it sits there and it looks up, it has this enormous field of view. So this is the entire sky, and it sees this sliver of the sky, this sort of cigar of the sky as the sky drifts overhead. And so it sees each patch of sky for roughly 10 minutes every day as it drifts overhead every single day. And so it forms, 1,000 pixels roughly on the sky, and we search all of them every day for fast radio bursts. And CHIME is crushing it. CHIME is doing remarkably well at finding FRBs. Just how well is nicely illustrated in this lovely plot. So sorry for the, sorry for the image quality, but I think this illustrates it very nicely. So the inset is just sort of the number of papers that have come out related to FRBs. So you can see this field is really growing. But what I want you to look at here is, observations over time. And, this is a different version of the plot I showed before. And here is where CHIME turned on and started reporting FRBs. So the reason that this flattens out is because we've only published a subset of the FRBs that we have found. So CHIME, just this year, released our first fast radio burst catalog. So in that catalog, we published 535 new FRB detections. So this was, at the time that this catalog came out, there were something like 150, 160 FRBs that had been published. So this more than quadrupled the sample of FRBs out there, which was an amazing initiative by, as you can see, an enormous group of people who worked very hard. I only joined the collaboration a year ago, so I'm not going to take any credit for any of this. This is all the hard work of all of these people who made this instrument work and did all of the really detailed and really interesting analysis. And on top of this, not only did we publish, our large sample of FRBs, we also had some very interesting and important companion papers that were all led by PhD students in our collaboration that did different interesting things with the catalog. So, once you have a large enough sample of FRBs, you can actually start to look at their distribution, look at their properties, look at patterns, trends. And that's exactly what our students were working on as part of their PhDs. And I won't have time to go into all of these papers, but I will just kind of highlight. So this is where we were at, like a couple of years ago. And then CHIME comes along and, all these gray dots are CHIME. So this is everything else before then CHIME just, blows it all out of the water, which is very exciting. So with this large sample, you can start to say interesting things. So for example, I think one of the most interesting things to come out of this catalog, and the only one that I'm going to touch on now, is looking at the signatures of each individual fast radio burst. I mentioned that we have lots of FRBs that we've only seen once, and then we have this subsample that we've seen to repeat. And so from the repeaters, you get a large sample of bursts. From the one-offs, you just get the one. But you can start to look at the distributions of these things, and you actually look at the sort of the fingerprint of each of these bursts. So if you look at them over the entire sort of spectrum that we see, what's being shown here, and this is work by one of our now graduated students, Dr. Ziggy Plunas, is that for the one-off FRBs, they seem to have a spectrum that's mostly sort of all the way across our observing bandwidth, sort of straight and narrow. And then for the repeaters, they have a more complicated, sort of smudgy appearance. And if you actually look at these in bulk, you look at the aggregate sample, which is something that we couldn't do before, you see that the one-off events sort of cluster in terms of, they cluster in one area of this parameter space of like how broadband are they and how long do they last? And the repeaters live in a totally different space. So we're actually starting to see that repeaters tend to have larger widths, smaller bandwidths. The actual specifics of that is not particularly important. It's just to say that with the CHIME sample, we can actually start to see, okay, repeaters actually appear to be, in some ways, phenomenologically different from one-off FRBs. So maybe they're truly separate, or they're the same type of emission mechanism, or they're the same type of source, but the way that they're generated is slightly different. That's causing them to look different in our data. This is, so this is very exciting. This is the first time we're able to see something like this in a large sample of FRBs. So the catalog has been really fundamental for our understanding, and there's only more to come from CHIME, of course. But I also want to flag another very important and interesting thing that CHIME saw. So since CHIME FRB has been in operation, it just stares at the sky every day. We're looking for fast radio bursts, but sometimes you find something you don't expect. And that was the case last April when CHIME FRB detected a super, super bright pulse from a galactic radio pulsar. And this is actually from a galactic magnetar. So magnetars are neutron stars, just like normal radio pulsars, but they have very strong magnetic fields relative to the normal pulsar population. And we don't see them often in radio. So we mostly see them in X-rays, just because they're more energetic. They emit in a slightly different way. But this one magnetar gave off an extremely bright radio pulse. And it was seen with CHIME. It was seen actually, so CHIME looks straight up at the sky. The source was very far off from the place where CHIME was looking, but it was so bright that it came in sort of through like a side lobe, we say. So it was actually, it's kind of seeing like something out of the corner of your eye, but it was so bright that it was immediately visible. It was actually seen at another telescope that we were using, the ARO, Algonquin Radio Observatory, and also in Canada. And it was seen by another instrument called STARE-2, which is located in Southern California. So this extremely bright radio pulse was eventually, actually quite quickly, identified by the CHIME team and by the STARE-2 team as coming from a magnetar called SGR 1935 plus 2154, but a galactic source. And this source was very interesting for a few reasons. First of all, this is possibly the brightest radio pulse we've seen from a magnetar. And also, it looked kind of FRB-like. So this started to get us kind of excited. So there are some theories for how this exactly happened, that maybe you have this magnetar and you get a giant flare that produces radio waves and X-rays. So I should also mention that it was detected in the X-rays around at the same time. It was active at radio and X-ray frequencies, so it was very closely studied by lots of teams. But this actually started to get us thinking that maybe in some cases, if you just get a really energetic event from a magnetar, that maybe it is like an FRB, or maybe it could be seen from another galaxy like an FRB. And this is starting to be supported. So this is kind of a complicated sciencey plot, but what's basically being shown here is on the y-axis, how bright is the thing and how fast is the thing. So neutron star radio pulses live here. FRBs are same sort of duration, millisecond duration, but very, very, very bright. And what's important, I'll flag, is that all of these pulses were radio pulses seen from SGR 1935, the galactic Magnetar. And first there was this really bright pulse, and then it was followed up with other telescopes, and we saw other pulses from it. And these are pulses from repeating fast radio bursts in other galaxies. So the most nearby sources we know, I should mention, these are some of the closest sources we have. So, they're not representative of the larger FRB population. But this is starting to fill in this, this is a thing I talked about. We know that, neutron stars, mostly emitted radio, they give off radio pulses. They're very extreme. And I mentioned before that they're definitely not strong enough to be seen from other galaxies, but maybe that's not always the case. Maybe some magnetar flares are convincingly FRB-like. And in fact, lots of people are saying, okay, they've got to be FRBs. But it's, magnetars have to be the explanation for FRBs. But it's worth remembering that there's a large sample of non-repeating FRBs from CHIME FRB. And there's also a repeating sample that look very much like this galactic magnetar. So we have, two potential pictures, cataclysmic, repeating. And honestly, like some of the discussion that happens within the FRB community at the moment is, why not both? Why can't we have both? Why can't both things be responsible for FRBs? Maybe some of them are repeating, some of them are cataclysmic, or maybe there's just some difference in phenomenology that leads to these different kinds of observed phenomena. So, we still need more FRBs. I'm going to probably keep saying this forever, but we also need to know where they're coming from. So what I haven't touched on in this talk is that we also are starting to identify host galaxies for fast radio bursts, but only a very small subset, something like 15 FRBs so far have known identified host galaxies. And the reason that this is challenging is because from the radio burst itself, it's hard to zoom in on where it's coming from. You really need to be able to kind of bullseye or like pinpoint exactly where the source is coming from on the sky. You need very high resolution information from the radio pulse. And this has been very hard to do for a long time. I mean, even high resolution radio data is hard to acquire in general, and trying to do it for something that lasts 5 milliseconds we're only really just starting to get there. But we will be able to do this more in the future because we have this really exciting initiative happening with CHIME FRB called Outriggers. So the CHIME FRB telescope, sorry, this is a little low quality, but the CHIME FRB telescope lives here in Penticton. And thanks to some funding in the US from the Gordon and Betty Moore Foundation, we're actually building 3 mini chimes at various distances from the big chime. And these outrigger stations are going to be sort of tilted to look at the exact same sky that CHIME is looking at as the sky drifts overhead. And these should be sensitive enough to see fast radio bursts that CHIME sees. And using the information that we get from the different telescopes and being able to sort of use these baselines in a technique that we call interferometry, we should be able to pinpoint exactly where on the sky these sources are coming from to the precision needed to identify their host galaxies. So when I joined CHIME, we were, talking about outriggers, and we had these nice pictures of, we're going to have mini chimes. This is what they're going to look like. But we've broken ground. We've started construction. We have our first mini chime basically ready. This is at Allenby, which is very close to the original CHIME site. And we're building 2 more that look just like this, but at a slight tilt in 2 locations in the United States. So this is going to be, I think, the next step in FRB science, is being able to find the large population that CHIME sees, but then couple that with finding all of the host galaxies using the CHIME FRB outriggers. So this is a very exciting new space, and probably there will be lots to say here in the next year or so once the outriggers start collecting data. So just to recap, I'm running out of time, I'm aware. So we've gone from having this one sort of mysterious, unknown Lorimer burst to having this massive population of FRBs over the whole sky. We still don't really have a lot of answers about, are they cataclysmic, repeating? Are they all the same? Exactly where are they coming from? But CHIME is playing a huge part in answering these questions and is going to continue playing a huge part, not just in CHIME itself, just searching and finding hundreds of new fast radio bursts a year, but also from the outriggers, where we will get hundreds of FRBs per year and host galaxies. And we'll start to be able to say something very interesting about, the larger sample of FRBs. So it's a very interesting time. So we still have lots of questions about where FRBs are coming from, what are they? But we're on the verge of exploring a whole new parameter space, answering these questions and no doubt asking new ones. So I hope this was interesting and you have questions. I hope you can ask some questions, but thank you for listening.
Thank you, Emily. That was a great talk. Super interesting. I really love the microwave story. It's one of my favorites. I was wondering, you explained how those fake bursts were distributed around lunchtime. Did you actually check? I don't know if that works, but did you try opening the microwave and then run to the telescope and see if you can see it? Did you test that?
Yeah, we did. Yeah, because we wanted to make sure that was actually what was causing it. And I wish I'd put the picture in my talk, but we actually, we did an experiment day where we pointed the telescope towards the location where we normally were seeing the peritons, because we also had information about where the telescope was pointing. And then we had site staff go around and test all the microwaves and just try different ways to make peritons. And in the end, that's how we figured it out. Was one of the site staff tried opening the door of the microwave before it was done. And we, were watching the data come in real time, and we saw the peritons. And we said, okay, that's it. We know what it is. Let's not do that anymore.
Okay. All right, we'll move on to audience question. So someone asked if you could actually hear fast radio bursts, let's say in your car radio. Would that work?
Oh, that's a really good question. Yeah, it's tough to do. It is possible. So it is possible to hear a pulsar, for example. You can configure the telescope data that comes out in such a way that you can hear all the pulses from a radio pulsar. Because what it is it's basically just this peak. It'll sound sort of like a boop. And you could, but fast radio bursts, it's worth mentioning, even though we see them at our telescope as being extremely bright and extremely obvious, in actual human terms, they're very faint. So we need very specialized equipment that has to be tuned very sensitively to be able to pick them up over the noise of our own electronic devices like cell phones and Wi-Fi and stuff like that. So if you configured a radio telescope in such a way that it output as a sound, you could probably hear the FRBs. But from a car radio, I think they're probably a little too faint.
Okay, so it's not what I was hearing the other day when my radio wasn't working. It wasn't the thousands of FRBs happening every day.
No. Although when you do hear static on the radio, sometimes that is the cosmic microwave background. So there's still astronomy happening in the car radio.
Okay, another question. There's the famous 1977 WOW signal, it's called.
Yeah.
Do you think that could have been an FRB?
Yeah, that's a good question. We've thought about it. It's not clear. The WOW signal is different from FRBs in that it lasted if I remember correctly, it lasted several minutes. So it was also in a similar type of survey where the sky was just drifting overhead and the telescope was listening. And the telescope picked up this very, very bright signal on its sort of chart recorder type thing. But the WOW signal lasted for for a few minutes, I think. So FRBs have only been observed sort of millisecond duration at the most. So that may have just been a different kind of anomaly that we still don't really know. But I don't think we think the WOW signal is an FRB. That would be amazing though.
Yeah. Okay, another question. Would it help to have some sort of equipment telescope in space to observe these FRBs and understand where they're coming from?
In a way, it would. So radio light gets through the Earth's atmosphere, no problem. So ground-based instruments work fine for searching for radio pulses. The problems that we run into searching for them on Earth is that human radio interference is so loud a lot of the time. We have to build our telescopes in these very specialized radio quiet remote sites, and even then we still get interference from airplanes and satellites and cell phones and GPS and all that stuff. So in some sense it could be a much quieter environment to build to put a radio telescope in space to search for FRBs. The one disadvantage is that you're limited in how big the telescope can be. And since you want as much collecting area and as much sensitivity as possible to see FRBs, on some level, it's better to just build on the ground and build something with that's really sensitive and can pick up a lot of signals. There are some radio telescopes in space, actually, and they're mostly used for interferometry, like I mentioned at the very end. But I'm actually not sure if anyone's been using them to look for FRBs. It would be a very interesting thing to do.
It would be, yeah. We'll check.
Yeah.
Okay, a bit of a technical question here. If the conical lighthouse beam is reaching the Earth and is coming from, let's say, the LMC, Large Magellanic Cloud, what would be the diameter? That's what the person is asking. Yep. What would be the diameter of that cone as it's coming across the Earth?
Yeah, that's a really good question. I don't know that off the top of my head. The pulse itself takes, of order a couple let's say 10 milliseconds to sweep across the entire Earth. And it's traveling at, it's sub speed of light. It's these pulsars are rotating at kind of close to the speed of light, maybe like a 0.1 times the speed of light or something like that. They're rotating very fast. But the cone, the beam itself, as it traverses Earth, is going to be extremely narrow. These pulsars have very, very narrow beams. So it's probably going to be not like AU size, but don't know the exact diameter off the top of my head, but that's a really cool question. I should work that out. I'm going to say it's not going to be AU, but it's going to be like probably hundreds of kilometers, thousands of kilometers. If there are pulsar astronomers in the chat, hit me up.
Another thing we'll check, and then we can answer people in the YouTube chat later.
Yeah.
Could you go back to the slide where you were showing the different positions where all the FRBs have been observed? Someone is asking about that. I think that's the one. This one. So it seems that there's kind of a hole. There's less FRBs in, let's say, minus 60 degrees. Do we know why that is?
Yeah, that's a great observation. It's entirely biased based on what telescopes we use to observe. So you'll notice that all of the CHIME bursts are concentrated over here with a particular concentration here. It's because the way that this is plotted, the coordinates it's in is sort of galactic coordinates. You could think of the Milky Way, the main spiral arm structure of the Milky Way is living along this 0 degrees line with the galactic center over here. And so this area, hopefully you can see my mouse, where all the CHIME events are, that's the northern hemisphere. That's, because our Earth is tilted with respect to the galactic plane. So this is the northern hemisphere. This is the southern hemisphere. So CHIME is doing great in the north. It can't see in the south. And then in the south over here, we're just kind of limited by where the telescopes are looking. So, I think it's, what we're seeing here is where have telescopes looked? FRBs are happening all over this map. It's just where have they been detected? They've been detected where the telescopes have been looking. And just based on the surveys that we've been conducting, we're biased against finding FRBs in here just because we haven't spent as much time. So it's not a real effect, but it is striking. I agree.
Yeah. About the other mini CHIME antennas that you showed, did you say that the one that is at Allenby, is it already operating? It's built, but is it running?
It is under construction. So you'll see that there's still some pieces missing. These are fresh photos taken today by one of our scientists, Jane, who's out there working on site. So these are the latest and greatest photos from the Allenby outrigger. So it's still missing some of the mesh. And they still need to put in the receivers that go along the focal plane. but it is under construction and we expect first light pretty soon. So
Awesome.
yeah.
Looking forward to see the results.
Ooh, me
And can
too.
you explain once again, you said that the reason you're building these mini telescopes is to be able to identify where the bursts are coming from. Why
Yeah.
is that the case? Why can't you do that with the original telescope?
Yeah, it's a good question. So let me go back to the CHIME picture that I showed. Yeah, this one. Okay, so CHIME looks over a large patch of sky, but each of these pixels or beams that it uses to look. So, we're kind of in radio astronomy, we're kind of limited because of, antenna physics for like what kind of resolution we can achieve with our telescope. So we get these beams, but they're actually quite large on the sky. You can say that an FRB happened in one of them and that gives you a certain level of precision, but it'll give you a pretty big error region on the sky and say the FRB came from somewhere in here. And that's, there's so many galaxies out in the universe that in that, even though it's kind of tiny, if you look deep enough, there's just tons of galaxies. So you can't say for certain just from that information exactly which galaxy it came from. The resolution of the instrument is not great enough. You're just not getting like the pixel resolution that you need. But what we're going to be doing with the outriggers is that there's this technique in radio astronomy called interferometry. And it's kind of technical, but the way that it works is that if you have different telescopes that are separated on something that we call a baseline, so, there's 3,300 kilometers between CHIME and let's say the Green Bank telescope. If we see the same FRB at both places, there's going to be a slight delay between the detection at each of those telescopes because of just where they're located on the sky and the speed of light and the way the Earth is rotating. And you can use that teeny tiny delay. It's a nanosecond delay sometimes. You can use that very short delay to actually get better resolution on the sky. So it's a kind of like radio astronomy like black magic, but it does work. And you can say, that narrows you down in like one dimension. You can say, okay, based on the delays, we can say something more precise about where it came from on the sky. And then you can use your other baselines. If you see the same FRB at CHIME and Allenby and Hat Creek and Green Bank, you can use all of those delays and all of those baselines to really tighten up the error region of where that FRB came from. And in some cases, you can do enough to actually say, okay, I know exactly where in the host galaxy it came from. I have such a small pinpointed error region that when I look on the sky in like an optical image like here, it's very clear that there's just one galaxy and that it lives in this part of this galaxy. But just based on the observations that we take with CHIME alone, we can't achieve this kind of resolution. So we actually need the other baselines to be able to say something more precise.
Yeah, and I'll mention for our regular viewers that have attended previous public lectures about, for example, LIGO. That's the same method that they use, right, to localize where gravitational waves are coming from. Yeah. Okay, so it's 8 p.m. We'll do one last question. You showed the many radio observatories that are used to observe FRBs. One of them was Arecibo, actually.
Yeah.
And Arecibo is unfortunately not in use anymore. It's destroyed. So how did you feel about that? And has it had a big impact on the FRB community?
Yeah, it was really sad. So I've never been to Arecibo, which was like one of my great regrets. I've always been planning to go visit, and sadly not possible anymore. The FRB community has a lot of pulsar astronomers in it as well. This as I kind of explained in my story, this community really came out of the pulsar community, and Arecibo has a very, very central place in the pulsar community heart because it's been used for decades to do very sensitive and very important pulsar observations. Even on the FRB side, Arecibo found the very first repeating fast radio burst, took some of the most sensitive measurements we've ever made of individual FRB sources. It wasn't a great FRB finding machine because it had such a small field of view on the sky, but it gave us some of our most sensitive FRB data that we've ever gotten. Now we have FAST, the 500 meter aperture spherical telescope in China that is kind of taking on a lot of what Arecibo was doing before. But Arecibo's loss is definitely felt very deeply within our community, and Arecibo played such an important role in the early days of FRBs, and you know, many of us were still using it. So yeah, it's very sad to us. Yeah, I mean, it was tough. It was a very tough time for radio astronomers and pulsar astronomers and FRB astronomers when we, you know, found out about Arecibo. So it's definitely played a big part, and you know, I think that's a very nice legacy for the telescope.
Definitely. Yeah, thank you for that heartfelt answer. Unfortunately, that's all the time that we have. So thank you everyone so much for all your questions. Please type your thank yous in the chat. You can also react on Zoom. Emily, that was a fantastic talk. I'm sure everyone enjoyed it. And we'll see everyone next month for our next public lecture. Thanks, everyone.
Thanks.
Bye-bye.